Hi guys, Miss Burns here, and today we're going to look at section P.3 in our textbook, which is on radicals and simplifying radical expressions. It's a really important section. We're going to use these rules quite a bit throughout the course, so I want you to get comfortable with the rules. If you haven't already done so, download the guided notes that go with section P.3. You'll want to save those, even if you don't print them. Think you'd probably want to go ahead and have them, but you can also write this on notebook paper. Make sure you leave yourself plenty of room. Before we get started, I want to remind you of the first maybe 10 or so perfect squares, because we're going to use these to simplify anytime we're working with a square root, like the first example. So I'm going to just kind of jot these off to the side. And what I mean by a perfect square, so say for example 1 squared is 1, 2 squared, 2 times 2 of course is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, and 10 squared is 100. These are the numbers we're going to use. So when we're looking at simplifying something like the square root of 500, what you want to do is think about which of these numbers is a factor of 500, and you want the largest perfect square. So if there's more than one, you want to pick the largest. So hopefully you notice 500, of course, 100 goes into that. So I'm going to write this as the square root of 100 times the square root of 5. Well, the square root of 100, since that's a perfect square, that's 10. 5 cannot be broken down. There's nothing else that goes into that. That's a perfect square, so I'm going to leave it as the square root of 5. And that's the simplified version of the square root of 500. Let's try the next one. We're multiplying the radicals square root of 6x times the square root of 3x. So if I multiply those together, we can multiply what's underneath radicals. So that's going to give me the square root of 18x squared. And then if you can simplify that, you want to go ahead and do so. So 18, we can simplify that. What number in this list goes into 18? That's a perfect square. Hopefully you notice that's 9. So I'm going to write the square root of 18 as the square root of 9 times the square root of 2, because 9 times 2 is 18. Square root of 9 breaks down to 3. 2 does not break down any further because none of the numbers in this list, other than 1, but 1 goes into everything, so that doesn't help. But there's nothing else in this list that goes into 2. So I'm going to leave that as the square root of 2. And then don't forget about the x squared. So the square root of x squared, we can break that down. Since that's a perfect square, that's just going to be x. So the 3 and the x are going to be outside of the radical. The 2 is going to stay under the radical. So if we clean this up a little bit, remember this was all multiplication. We have 3x times the square root of 2, and that's the simplified version. Letter C, we're dividing the square root of 100 divided by 9. So there's a property with radicals that says we can separate, just like we can separate multiplication, we can also separate division. So I'm going to rewrite this as the square root of 100 divided by the square root of 9. And then simplify each of those on their own. They're both perfect squares, so the square root of 100 is 10, the square root of 9 is 3, and that's our final answer. All right, let's take a look at example 3. So square root of 11 on its own, of course, doesn't simplify since 11 is a prime number, and square root of 5, same thing. Neither one of those simplify. But there is a rule, if you remember from high school algebra, that says you cannot leave a radical in the denominator. And so one way to get rid of the radical, the square root of 5 that's in the denominator, is to do what's called rationalizing it. And the way we're going to do that is we're going to multiply the top and bottom of this radical by the square root of 5. And the reason we can do that is because we're essentially just multiplying it by 1. Root 5 over root 5 is 1. So we can always multiply a fraction by 1. That doesn't change the value. So then in the numerator, we're going to multiply the radicals square root of 11 times the square root of 5. That gives us square root of 55. The denominator, the square root of 5 times the square root of 5, is the square root of 25. But notice that's a perfect square, isn't it? The square root of 25, of course, is just 5. So we have the square root of 55 divided by the square root of 5. Divided by 5. And that gets us so that we don't have the radical in the denominator anymore. You could just go right to that step. When you multiply square root of 5 times the square root of 5, you can just say it's 5. You don't have to go through this intermediate step, but I want to make sure everybody sees that that's really the square root of 25, which is what leaves the 5 in the denominator. Let's try letter D. We're going to have to rationalize the denominator, but I would suggest if you can simplify any of the radicals, you do that in the beginning. So if you notice the square root of 8, we can break that down because what number in our list of perfect squares goes into 8? And hopefully you see that that's 4. So off to the side here, I'm going to write the square root of 8, and I'm going to break it down into the square root of 4 times the square root of 2. And square root of 4 is our perfect square. You notice when I simplify these, by the way, I always put the square root factor first. I did that up here. I put the 9 in front of the 2. I put the 100 in front of the 5. I think if you get in the habit when you simplify these of putting the perfect square first, I think that'll make it a little easier to simplify. So that gives me 2, because the square root of 4 is 2, times the square root of 2. So let me come back to the problem here. Then we have 12 divided by 2 times the square root of 2. So I replace the square root of 8 with 2 radical 2. You notice the 12 and the 2, since those are outside the radicals and they both have a factor of 2, we can reduce them. So 12 divided by 2 is 6. 2 divided by 2 is 1. So now I have 6 divided by the square root of 2. And we still have to rationalize that. So I'm going to multiply the top and bottom here by the square root of 2. Just like I did over here, I multiplied by radical 5 on the top and bottom. So I'm going to multiply radical 2 on the top and bottom. And let me circle this so we know that that's separate. Let me come over here and write what we have now. So we have 6 times the square root of 2 in the numerator. In the denominator, we have square root of 2 times the square root of 2, which is really the square root of 4, but of course that simplifies to 2. And check at the end just to see if there's any other reducing you can do. Notice anything outside the radical can be canceled if it can be simplified. So we have a 6 here and a 2 here. 6 divided by 2 goes 3 times. 2 divided by 2 is once. So that leaves us as 3 times the square root of 2 as our simplified answer. And notice we don't have any radicals in any denominators. All right, take a look at example 3. This time we're adding and subtracting. So when you add and subtract radicals, they have to be like terms. That's very important. It doesn't have to be, they don't have to be like terms when we're multiplying and dividing, but when you're adding and subtracting, the radicals must be like terms. And the way we combine them is just like we would combine any other like terms. So we have 7 times the square root of 2 plus 5 times the square root of 2. Since they're like terms, we're going to go ahead and add the coefficients. So how many square roots of 2 does that give me? That gives me 12 times the square root of 2. We don't add the radicals together. It's just like combining like terms. It stays square root of 2, but we have 12 of them because we added the coefficients together. Letter B is the same type of question. We've got the square root of 5x minus 7 times the square root of 5x. They're like terms because they both have square root of 5x under the radicals. This is basically a coefficient of 1 in the front. So we have 1 take away 7 gives me negative 6 times the square root of 5x. And those are simplified. Notice in letter C, it's not quite as straightforward. We're adding and subtracting, but these are not like terms. However, you might notice they can all be simplified. So let's go through and simplify each term and see if we have any like terms we can combine at the end. So let's start with the square root of 54. So 54, is there anything in our list of perfect squares that goes into 54? And hopefully you see that that would be 9. So I'm going to write 54. I'm going to come over here and write this. I'm going to write the square root of 54 as the square root of 9 times the square root of 6, because 9 times 6 is 54. So the square root of 9 breaks down into 3 times the square root of 6. Now notice there was a 3 in front of this radical, so 3 times the square root of 54. So I have a 3 in the front. So then that 3 in the front, that coefficient of 3 times the 3 that I simplified can be multiplied. So that gives me 9 times the square root of 6 for that first term. Let's look at the 2 square roots of 24. So let me come over here and write 2 times the square root of 24. 24 will break down using a perfect square from our list. 4 will go into it. So I'm going to write 24 as the square root of 4 times the square root of 6, because 4 times 6 is 24. And that leaves me with 2 times the square root of 6. Notice we had that 2 in the front though. So those coefficients can now be multiplied. So that gives me a minus 4 times the square root of 6. 96, can we break that down? Let's see, I didn't leave you a lot of room on the paper here. Let me write this one on the back. Negative square root of 96. So let's write this here, square root of 96. So is there anything in our list that goes into 96 from our list of perfect squares. And you can use a calculator to help you if you need to with the numbers, but you'll notice that 16 is a perfect square, and that goes into 96 6 times. So we have the square root of 16 times the square root of 6. So that breaks down into 4 times the square root of 6. So let me come back over here, and I'm going to insert that back into the problem. So we have minus 4 times the square root of 6. Just a coincidence that those two were the same, but 4 times the square root of 6 and 4 times the square root of 6. Let's do the last one, square root of 63. So I'm going to write this on the back, square root of 63. That breaks down into 9, I believe. 9 goes into 63 7 times. So that's the square root of 9 times the square root of 7. So that breaks down into 3 times the square root of 7. This had a coefficient in front. I didn't write that, but it was a 4. So let me go back and write that. So we had a 4 in front of this expression. So that 4 and that 3 can be multiplied. So that gives me a 12 times the square root of 7 for that last term. So we're going to have minus 12 times the square root of 7. Now look at what you've got. Anything that's a like term, we can go ahead and combine it. So 9 square roots of 6, take away 4 square roots of 6 is 5 square roots of 6. Take away 4 again is 1 square root of 6. So we've got 1 square root of 6, so there's an implied 1 in front. The 7, there's nothing else to combine that radical 7 with, so we have minus 12 radical 7. And that's as simplified as that gets. Let's take a look at example D. So we have 4 times the square root of 50x minus 6 times the square root of 32x. So the 50 and the 32, I know I need to break down because there's numbers in our list of perfect squares that will go into both of those. I'm going to write this on the back so I have some more room. So we had 4 times the square root of 50x. Let's just start with that. We can break the 50 down into the square root of 25 times the square root of 2. And that breaks down into 5 times the square root of 2. Don't forget, though, we had the 4 in the front. And by the way, the x was still under the radical. I did not do anything with that. So there's still a square root of x remaining. So the coefficients can be multiplied. So we have 20. And then what's underneath the radical, the 2 times the x are still remaining. So 20 times the square root of 2x is what that simplifies to. So I'm going to fill that in and write 20 times the square root of 2x. Now, if we can get this other term to simplify the same way, and if they're like terms, then we can combine them. So let's check. We have 6 times the square root of 32x. So 6 times the square root of 32x. So I'm going to just work with the 32 for a second. I'm going to break that down. Notice that 4 goes into 32, but so does 16. So when you simplify these, you want to pick the biggest perfect square that goes into that number. 4 will work, but 16 is better. If we use 4, we're going to have to simplify it again. So if you pick the biggest perfect square factor, then you're only going to have to simplify it the one time. 16 times 2 is 32. So that breaks down into 4 times the square root of 2. Don't forget about that 6, though, that we had in the front. He's still sitting there. So, and then also don't forget the square root of x that we still have under the radical. That can't be simplified because it's just an x. So we're going to have 24 in the front, and we're still going to have the 2 and the x multiplied together under the radical. So let's go ahead and put that back in and see what our final answer is. So we had minus 24 times the square root of 2x. And you notice those are like radicals, so we can go ahead and combine the coefficients. Positive 20, negative 24 gives me negative 4 times the square root of 2x. And there's our final answer for that. We take a look at example 5. Now we're getting into cube roots. The process is very similar for simplifying them. The difference, though, is we want to look for perfect cube factors and not perfect square factors. So over the side here, I'm going to make a quick list of the first maybe 5 perfect cubes. So in 1 cubed, I always just start my list with that. 1 cubed, of course, is 1. 2 cubed is 8. 2 times 2 times 2. 3 cubed is 27. 4 cubed is 64. And 5 cubed, 5 times 5 times 5 is 125. Which one of those numbers goes into 24? And that would be 8. So I'm going to write this as the cube root of 8 times the cube root of 3, because 8 times 3 is 24. 8 is a perfect cube, so the cube root of 8 breaks down. What is the cube root of 8? and that would be 2. 2 times 2 times 2 is where the 8 came from. 3, nothing goes into this list. That's a perfect cube. 3 is a prime number, so it doesn't break down, so that stays as the cube root of 3. So we have 2 times the cube root of 3 is our answer. Letter B, we're combining like terms again. If we can do so, we have to see if we can simplify these radicals. So the cube root of 16, what number in our list goes into 16? Once again, that's 8. So I'm going to write the cube root of 16 as the cube root of 8 times the cube root of 2, and there's a 5 in front, so I'm going to bring that down. Cube root of 8 times cube root of 2, 8 times 2 is 16. So that's 5 times 2, because that's the cube root of 8, times the cube root of 2. So that gives me a coefficient of 10 times the cube root of 2. Now the other term, we had 11 times the cube root of 2. Cube root of 2 does not break down. 2 is a prime number. So I'm just going to bring that down. So we have minus 11 times the cube root of 2. Now those are like terms, so we can combine 10 minus 11, and we get negative 1 times the cube root of 2 as our final answer. So I left the 1 out because it's just a 1, but there's a negative because it's 10 minus 11. The last section, we're looking at fractional or rational exponents. Pay really close attention to these exercises. This is going to come up several times throughout the course, and the more comfortable you are with working with these exponents, the easier things are going to be later on. I think in the P.2 section we had a list of properties for exponents, and I believe this was on the list. One of those properties, it may not have been, I'm not sure, so let me give you the rule here. If you have a fractional exponent, so an exponent that's a fraction, one way you can simplify that is to convert it to a radical. And the rule for converting it looks like this. If I have x to the m over n power, so if I have x raised to the m over n power, I can rewrite that as the nth root, so the denominator becomes the root of the radical, of x raised to the m power. And that's the rule you want to get really, really comfortable with. So let's see how that applies to these problems. So we have 27 to the 2/3 power. So I'm going to first write that using this rule. I'm going to write that as a radical. So the denominator becomes the index of the radical. So I have the cube root of 27 to the 2nd power. The nice thing about these is you can do this, you can simplify this in one of two ways. You can either do the cube root of 27 first and then square that number, or you can square that number and then take the cube root. I think it's generally easier to take the root first because you're working with a smaller number. So let's do that. The cube root of 27 is 3 because 3 times 3 gives us 27. So that means we have 3, but don't forget we still had that squared sitting there. So then it becomes 3 squared, which is just 9. So 27 to the 2/3 power is the same as 9. Let's try 64 to the 1/2 power. So I'm going to write that as a radical first. The denominator becomes the root of your radical. The numerator stays with the base that you're taking to a power. 2, of course, is the square root. We don't normally write the 2, and you could leave the 2 out, but I want to just emphasize that's from the denominator. So we're looking at the square root of 64 to the 1st power. So what is the square root of 64? And of course, that's 8 to the 1st power, which is just 8. Nice little rule of thumb, anything to the 1/2 power is always going to just be the same as the square root of that number. But just go through the process using this rule to rewrite it as a radical. Let's try letter C. We've got 9 to the 3/2 power. So I'm going to write that as the square root of 9 to the 3rd power. So the square root of 9, if we do that first, that gives us 3. And then we're still going to raise it to the 3rd power. So what is 3 to the 3rd power? 3 times 3 times 3. And that would be 27. Last one, there's a little extra thing here. It's got a negative exponent. So before you do anything, get rid of that negative exponent. And if you'll recall from the last section, P.2, we had a rule with exponents that said if you have x to a negative power, you can rewrite that as 1 over x to the positive power. And that's the rule we're going to apply here. So I'm going to write this as 1 over 81 to the positive 3/4 power. Then we're going to use the radical rule to simplify that denominator. So that gives us 1 over the 4th root of 81 to the 3rd power. The fourth root of 81, we could do 81 cubed first, but that's going to be a really big number. The fourth root of 81 is actually a nice number. It's an integer. If you use your calculator and figure it out, or you just kind of play with your numbers, you'll find that it's 3. 3 to the fourth power is 81. 3 times 3 is 9. Times 3 is 27. Times 3 again is 81. So that will simplify to 1 over 3 to the third power. Still, we have to take care of that cube. So it's 1 over 27 is going to be our final answer.